In today's video, we're going to look at the relationship between rational exponents and radicals. But before we can do that, let's review the properties of exponents as we'll be working with those in our future examples. Our general properties of exponents, a to the m times a to the n, when we have the same base and these are being multiplied, we add our exponents. A to the m divided by a to the n, when we have the same base and we're dividing, we subtract our exponents. We're taking the numerator exponent and subtracting the denominator exponent. The order does matter with subtraction. A to the m raised to a power of n. This is our power rule. Anytime you have a power raised to another power, we multiply those exponents. So this is a to the m times n. Parentheses, a times b raised to a power of n. When we've got two things being multiplied, inside the parentheses, we can distribute the exponent. So we get a to the m, b to the m. Be very careful, this is not true when you have a binomial in the parentheses. So for example, if you've got a plus b to the m, this is not the same as a to the m plus b to the m. Okay, be very careful with that. We're going to emphasize this with a sad face. A over b to the m, just like with the product inside the parentheses, when we have a quotient inside the parentheses or a fraction, we can distribute the exponent to the top and the bottom. So we have a to the m divided by b to the m. Next, we'll look at the properties involving negative exponents. In general, when we have a negative exponent, in order to make that exponent positive, we want to move that term to the other side of the fraction. So if I look at this first rule, a to the negative m, I can make this a fraction by putting it over 1. I then take the term with the negative exponent and I move it to the other side of the fraction, in this case the denominator, and that's what results in a positive exponent. Now in the second example, our negative exponent exists in the denominator. So to make the exponent positive, we take the term with the negative exponent and we move it to the numerator. So we have b to a power of positive m. I want to emphasize that in these two examples, we are not flipping the fraction at all. All we are doing is moving the term with the negative exponent to the other side of the fraction. I'm going to show you a brief example here where, just to re-emphasize that we're not flipping. If I've got x over xy to the negative 2 over z, the only term in this expression that has a negative exponent is the y to the negative 2. That negative 2 exponent is only on y since x and y don't have a parentheses around them. So what we want to do to make that negative 2 positive is take this and move it to the denominator of this fraction. So we end up with x over y squared z. Notice I didn't flip anything in the fraction. All I did was move the individual terms with the negative exponent to the other side. And lastly, the zero property for exponents, anything raised to a power of 0 is 1. Now there are proofs and justifications for these properties. I'm not going to go into those in this video, but if you're interested, you can research those on YouTube. Now that we've reviewed the properties of exponents, let's talk about rational exponents. Rational exponents are exponents that are fractions. And there's a relationship between a rational exponent and a radical. And that relationship is a to a power of m over n is equivalent to the nth root of a to the m. Notice the position of our the numerator and the denominator. The numerator is the exponent in the radical form, and the denominator becomes the index in the radical form. Now this can also be written as the nth root of a raised to a power of m. The only difference between these two expressions is the order in which we're going to simplify. In this first one, we're actually going to simplify a to the m first and then take the nth root. Whereas in this second one, we're going to simplify the nth root of a and then take that and raise it to a power of m. So all that we're changing is the order. And depending on the problem, one setup might be better or more useful than the other. Simplify by converting to radical form. Now when I look at this expression, many of us read it negative 16 to a power of 1/2. But what we want to make sure that we're very clear about dealing with our order of operations is that this exponent of 1/2 is only on the base directly in front of it. This negative is like a -1, is not grouped with the 16. It's being multiplied by that 16, which has an exponent of 1/2. If I wanted the negative to be attached to the 16, we would write it as negative 16 to the 1/2 power. So be mindful of that. When you have just a negative out front, unless it's connected to that coefficient with parentheses, it's not going to be included in the base for that exponential expression. So we simplify 16 to the power of 1/2 with the negative out front. To convert this to radical form, the denominator becomes our index, so it's the square root of 16, and then we have a power of 1 from that numerator value. Now 16 to the first power is 16. What is the square root of 16? It is 4, and that negative is still hanging out in the front. 5x to the 1/4. Again, we want to convert this to radical form, but here we have the same thing. That 1/4 is only on the x. So I can add some parentheses like that show a little bit more clearly that only the x to the 1/4 is going to be converted to a radical. The 5 is just going to be a coefficient out front. So we have 5. The denominator of my rational exponent becomes my index times the 4th root of x. And since my numerator was 1, there's no need of writing a power of 1. Negative 27 to the negative 2/3 power, or negative 1 times 27 to the 2/3. So we're really driving this point home that that negative, unless it's included in parentheses, is not going to be part of the radical expression. So the first thing that we want to do is fix this exponent, which is negative. How do I make an exponent positive? You move it to the other side of the fraction. So the negative is still hanging out in the front. And now I'm going to write this as 1 over 27 to a positive 2/3 power. Now as a direction state, I'm going to convert to radical form to see if I can simplify. So that negative is still hanging out in the front, 1 over. The denominator of my rational exponent becomes my index, 27, and then the exponent becomes our power. Now in this case, I'm going to put the 2 on the outside, because what I'm looking at here is the cube root of 27, and I know the cube root of 27, this is 3. So I can simplify that very quickly. If I first squared 27, I'd have to get a calculator out, and then I would have a very large number, which I would have to take the cube root of. It's a little bit more cumbersome. So we have negative 1 over, the cube root of 27 is 3 squared, which simplifies to negative 1 over 9. Nine to the 2/5 power over 9 to the 12/5 power. Notice in this expression we have the same base and our terms are being divided. So we're going to set up subtraction with our exponents. So this is the same as 9 to the 2/5 minus 12/5. Now if we notice here, we've got the same denominator, so we can combine those nicely. This is 9 to the negative 10 over 5, which we can simplify to negative 10 over 5. That's 9 to the negative 2. And you'll see in your homework and on test questions and on review questions, there's always going to be a bit that says, make sure you leave your answers with only positive exponents. It's not common form to use or to leave a negative exponent in an expression. So again, to make this exponent positive, convert this to a fraction by just putting it over 1, and then move this term to the denominator. Now when we move it to the denominator, we get 9 squared in the bottom. But what's left in the numerator? Again, think about a product up here. What times 9 to the negative 2 is still 9 to the negative 2? There's that invisible 1 right here. So we're left with a 1 in the numerator. And again, simplifying further because I can evaluate 9 squared. This is 1 over 81. The 10th root of y to the 5th. Now we're going to simplify the radical by converting to rational exponents. So before we had rational exponents and we converted to radical form, now we're just going to go the reverse route. So I'm going to take this y and I'm raising it to a fraction. The index becomes the denominator, the power becomes the numerator. So y to the 5 over 10, we're going to simplify that fraction. This is y to the 1/2. And I'm going to come back here and emphasize in the directions that we want to simplify the radical, which means I want my final answer to be, in fact, a radical. Now that I've simplified that rational exponent, we're going to convert back to radical form. The denominator of my rational exponent becomes the index. So this is the second or the square root of y to a power of 1. And since the absence of an index implies the square root, we will actually just write this as the square root of y. The 4th root of 9. Now if I look at this and I convert just to rational exponent, I get 9 to a power of 1/4. It doesn't really help me simplify this any further. So what I want to do is look at this radicand of 9. Is there another way that I could rewrite 9 as maybe a term with an exponent? Well, 9 is the same as 3 squared. So this expression is the same as the 4th root of 3 squared, which now we can convert this to a rational exponent. This is 3 to the 2 over 4 power. And now that fraction of 2 over 4 can be simplified. We get 3 to the 1/2 power. Again, simplifying the radical implies that we want to convert our answer to a radical back at the end. So this is the square root of 3. That's pretty neat. We found that the 4th root of 9 is equal to the square root of 3. The 9th root of a to the 6th n to the 3rd. It's telling us use rational exponents. So the first thing we want to do is convert from radical form to a rational exponent. I'm going to group these things together. Now the radical automatically groups the entire radicand together, but I'm going to show that we've got an exponent of 1 on the entire radicand. So first I'm just going to get rid of that 9th root. If I do that, I've got a to the 6th n cubed to a power of 1 over 9. The index became the denominator, the exponent the numerator. Now we're starting to use our properties of exponents. A to the 6th and n cubed are being multiplied inside the parentheses, so we can take that exponent and distribute it to both terms. Now I'm going to add some more parentheses here because I've got a to the 6th being raised to a power of 1 over 9 times n cubed being raised to a power of 1 over 9. It's important that we see those parentheses because then we're utilizing a new property, power to a power. What do we do with those exponents? We multiply them. So this is a, doesn't look like an A, it looks like a 9. This is a to a power of 6 over 9 times n to a power of 3 over 9. And when we look at these fractions, we recognize that we can simplify both of them. So this is a to the 2/3 power times n to the 1/3 power. And now we want to convert back to radical form. Since they both have the same denominator, we know that that's going to become the index. And then what's left underneath the radical? Or yes, what's underneath the radical? We've got a to a power of 2 times n to a power of 1. Now, some people might look at this, and rather than adding these parentheses here, they kind of take a shortcut. They're going to just take numerator, denominator, numerator, denominator. So a to the 6 over 9 times n to the 3 over 9. And you can see that that's the same step that we had down here. So it does skip a few steps, but I like this technique simply because it does illustrate those properties of exponents very well. Either one works just fine though. The square root of y times the cube root of y. We want to simplify these. Now, we learned in previous videos the product rule for radicals that we could just multiply underneath the radicals. But that required that we had the same index. And we see in these two radicals, one has an index of 2 and one has an index of 3, so we can't apply that property. That's why it says use rational exponents. So the square root of y is the same as y to the 1/2 power. The cube root of y is y to the 1/3 power. We use our property of exponents that says when we're multiplying with the same base, we add our exponents. So this is y to the 1/2 plus 1/3. We can add these two fractions. We just need to find a common denominator. So I'm going to do that over here in the side in my margin. My common denominator is 6, so I'm going to multiply the first fraction by 3 over 3, the second fraction by 2 over 2. So this is 3 over 6 plus 2 over 6, or 5 over 6. So this simplifies to y to the 5 over 6 power. And again, simplifying a radical indicates that we want our final answer written in radical form. The denominator of the rational exponent becomes my index, y to a power of 5, where the numerator of the rational exponent is the power. The cube root of x divided by the 4th root of x. This is very similar to the last example where we've got different indices, but we're still trying to work with something with the same base. So we start by converting to rational exponents. This is x to the 1/3 over x to the 1/4. And when we're dividing those two expressions, we're going to subtract our exponents. So this is the same as x to the 1/3 minus 1/4. Again, in my margin, we'll find a common denominator to combine those. So 1 over 3 minus 1 over 4. Our LCD is 12. So I'm going to multiply the first fraction by 4 over 4, the second fraction by 3 over 3. So we have 4 over 12 minus 3 over 12, which is 1 over 12. If I take this rational exponent and now convert it back to radical form, the index is going to be 12, or the 12th root of x. The square root of 5 times the cube root of 2. Following the directions, we're going to convert to rational expressions, even if it's not clear as to why. So we have 5 to the power of 1/2 times 2 to the power of 1/3. If you think back at a previous example, and I'll show it to you guys. I think it was this one, where we ended up with different bases, but they had the same denominator. When they had that same denominator in the rational exponent, we could pull that out in radical form as the index. We're going to do the same thing here. So looking at these two exponents, I want to rewrite them so that they have the same denominator. So if I think about 1/2 and 1/3, we're not combining these, but how do we get a common denominator? We're going to multiply this one by 3 over 3 and this one by 2 over 2. So this new fraction is 5 to the 3 over 6 times 2 has a new exponent of 2 over 6. Take a second, look back. We haven't changed anything in our expression. All we've done is rewrite those exponents so that they have the same denominator. 1/2 is equivalent to 3 over 6. 1/3 is equivalent to 2 over 6. But now that we have the same denominator in our rational exponents, that denominator becomes the index of our radical. So this is the 6th root of 5 cubed times 2 squared. Since we're dealing with numeric values here, we want to simplify further. This is the 6th root. 5 cubed is 125 times 4, which is the 6th root of 500, I believe. Let me check that. I don't know if that's right. You tell me. Check it out and let me know if there's something wrong with it. But I think it's good. Yeah, I think we're pretty good. In this case, if you could simplify, you would simplify further. I don't have a calculator with me, so you guys can try to find a perfect 6th. Remember that the index is 6. We're not looking for square roots, but 6th roots of 500. Okay, so just to recap, we looked at the properties of exponents and then we saw how that relates when we have rational exponents. The rules are exactly the same. They don't change just because now our exponents are fractions. Another key thing you want to remember, follow the directions in the problem. If the directions say use rational exponents, that's what you should do. If we start with a radical, first you want to convert to rational exponents. If it says simplify the radical, that means your answer should end up as a radical. All right, so our directions can help us out a lot in at least getting us started and seeing how we're going to begin a problem. In our next videos, we're going to look at solving radical equations and complex numbers. So we'll see you guys next time for that. Thanks a lot.